It is a Friday afternoon, and a data engineering team is running a routine cleanup script to clear out a temporary staging environment. But a slight typo in the code redirects the script away from the staging table and points it directly at prod orders fact. In an instant, the execution completes, wiping out 50,000 production rows. In a traditional on-premise database architecture, a dropped production table triggers an immediate multi-department crisis. The data is entirely gone from the active system. Engineers have to endure a heavy operational tax to get it back. They must track down the correct physical backup tape or storage volume, provision temporary servers to hold the restored data, and completely halt production workloads while the data is physically moved back into place. That heavy physical infrastructure is being replaced by a model that allows engineers to pull data from the past using standard declarative SQL. Snowflake achieves this through a native feature called Time Travel. It continually tracks the state of your data before every update, maintaining those historical versions as queryable snapshots. By treating historical data as an instantly accessible dimension, engineers eliminate backup-associated downtime and execute disaster recovery in seconds. To utilize this capability, we have to map out exactly how Snowflake configures data retention across its ecosystem. On a standard edition account, the default time travel retention period applied to all newly created tables is exactly 1 day, or 24 hours. This matrix shows how the limits scale based on your tier. Upgrading to Enterprise Edition expands that time travel retention window to 90 days for permanent tables. Engineers control this timeline directly by modifying a single parameter called data retention time in days. However, there is a strict architectural boundary that triggers the exact second the time travel retention period expires. The data immediately drops out of the time travel window and locks into a tier called failsafe. This is a non-configurable 7-day disaster recovery window. Once data enters failsafe, the SQL queries stop working. Users cannot access this data directly. Recovery requires an official intervention from Snowflake support. Maintaining historical snapshots generates a direct storage cost. The longer your retention period, the more physical storage overhead you pay for the accumulating historical states. If you reduce a table's retention parameter, say from 10 days down to 1 day, Snowflake immediately takes the data from days 2 through 10 and moves it straight into failsafe. Knowing the exact boundary between user-queried time travel and system-locked failsafe allows teams to calculate accurate storage costs and set realistic SLAs for data recovery. We can apply this to the problem from earlier. The prod orders fact table has been truncated. The structure is sitting in production, but it contains 0 rows. Here we use the first time travel extension. Adding the at clause and offset parameter points our query at the past. The offset calculates time in seconds. -3600 pushes our view back 1 hour, verifying the 50,000 rows remain intact. The standard approach would be to run an insert command, dragging 50,000 rows out of the snapshot and writing them into production. Instead, we use the highly optimized clone command, combining it directly with our 1-hour offset. This initiates a zero-copy operation. Snowflake doesn't physically duplicate the 50,000 rows of storage blocks. It simply generates a logical metadata pointer to the existing historical data. To bring the system back online, the engineering team runs an alter table command to rename the broken table and swaps the newly cloned table into its place. By pairing a temporal offset with logical cloning, catastrophic data loss becomes a lightweight metadata operation that executes and resolves in seconds. That capability extends beyond simple recovery and solves complex architectural challenges, like tracking silent data drift in a fintech compliance environment. Suppose a compliance team runs a daily report on regional account balances. Today, their query of yesterday's numbers produces a different total than the exact same report sent to regulators 24 hours ago. Someone updated rows in the table after the report was generated. In a standard relational database, tracking down exactly which rows mutated requires intensive architectural planning. Teams typically rely on secondary audit tables, driven by database triggers. This places a heavy, constant performance penalty on the system during normal operation. This SQL code bypasses audit tables by executing a temporal self-join. The first half defines the primary table, labeled cur, representing the current accounts. We then join it to hist, the identical table appended with the @timestamp clause. This precision locks the historical side of the join to the exact UTC execution of yesterday's report. The join condition aligns the current and historical account IDs row by row. Subtracting the historical balance isolates the exact numerical drift on changed accounts. Complex compliance auditing becomes a highly targeted, lightweight query time operation rather than a persistent write time burden on the database architecture. Time travel handles data manipulation errors like updates and truncates, but it also applies to data definition errors. An engineer might accidentally execute a drop command, deleting an entire schema or destroying an entire database structure. On the back end, Snowflake does not immediately purge those dropped objects. The architecture keeps them intact and visible within the system's history output. This tree diagram shows the final time travel recovery command in action. When a database is deleted, executing UNDROP database immediately reattaches the node. The object, schemas, tables, and all underlying data are instantly restored to the exact state they held milliseconds before the drop command was issued. Across all of these scenarios, the underlying mechanical advantage remains the same. This summary layout shows the three primary vectors for historical control: UNDROP to restore dropped structures, offset to bypass script errors and clone lost rows, and timestamp to audit precise regulatory changes. Snowflake fully decouples the safety of your data from the limitations of physical hardware and rigid backup schedules. By treating time as a native, queryable dimension of standard SQL, engineers can design highly fault-tolerant pipelines entirely free of legacy operational overhead.